Welcome to ECE 320A review session for exam number 3. Material, I hope this comes as no surprise to you. It's going to be over homeworks 6, 7, and 8. The topics, for a much longer list, look on D2L for the list of topics under the exam number 3 material. But really I'm sort of classifying it into 3 groups. One is the Laplace transform or Laplace domain circuits, S-domain circuits. The other is convolution. And the third is basically playing with h of s on the imaginary axis, or walking up the imaginary axis, both analytically and graphically. If we go back to Laplace circuits, or S-domain circuits, you need to be able to incorporate initial conditions with those circuit models, and you need to know the difference between the two types of sources that you can incorporate into those S-domain models depending on whether you want to use mesh analysis or write KVL equations, or whether you're wanting to write node voltage analysis or write KCL equations. Depending on which of those you might want to do or which of those you are asked to do, the problem may say, assume you are doing node voltage analysis. That's a big clue. Okay, I need to do current sources for my initial conditions. I need to incorporate my initial conditions as parallel current sources. You need to be comfortable doing either of those. If you're solving the problem yourself and it doesn't specify which one, you can do whichever one you want. But it may, as a problem, say, assume you're performing mesh analysis, or assume you're writing KVL equations. Then you need to incorporate your initial conditions in the form of series voltage sources. If you're given a Laplace or S-domain circuit or a time domain circuit and asked to find a transfer function, you should be able to do that. So you could quickly put it into the S-domain. You don't have to worry about initial conditions. You just replace all of these passive devices with their S-domain equivalents, and then find the equations necessary to get a relationship between your input and your output, and then find that ratio to get the transfer function. You may also be asked to put your equations in matrix form. Maybe I want to make it easier for me to grade, and you now have 3 KVL equations that you need to write. I might want you to write that as an impedance matrix that's 3 by 3, so you'll have 9 entries in that. A column of unknown current, mesh currents, I1, I2, I3, equaling some right-hand side made up of sources. It should be clear. And then I won't have to ask you to invert a 10 by 10 matrix, which the people with calculators can push a button and do. Those that don't can't, so I don't want that to be an issue. But I would like you to be able to formulate the problem so that if you had the machinery, you could solve it for those vectors of currents. And I hope it's clear what I'm talking about. So you should be able to write your equations in the form of matrix expressions, maybe not solve for the matrix expressions, but at least put the equations that are coupled sets of equations into a matrix structure. With respect to convolution, and we may go through some examples with this, I want you to be able to determine when you're going to start seeing some non-zero value at the output, when you will finally not see any more signal in the output. So what are your beginning and ending time intervals for the output that you can expect a non-zero output? I might just give you a generic waveform and say, pretend you are flipping and sliding this waveform. Draw it, label it, and show me what x of t minus lambda is For example, if I just gave you a generic waveform x of t, I might ask you to set up the convolution problem in all of its detail, but not solve the integrals. Which means maybe you find that there's 5 overlap patterns that are unique, then you would need to find the 5 intervals of time when those overlap patterns are true, and the integrals, both the arguments or the integrands and the lower and upper limit of integration in those 5 different overlap patterns. I may ask you to set that up, maybe not solve the integral. I'll assume you can do that given time. And if you had a calculator, you could just have your calculator solve the integral. So I'm not worried so much about solving the integral, but you should be able to integrate polynomials. You should be able to integrate exponentials. Some of the basic integrals you should be able to do. Maybe I won't have you integrate by parts 3 different times to finally get the right answer. And I might simply ask you, give me the output y of t at 6. So I might say, what is y of 6? That means you could do it the long way and solve the entire problem for all y of t and then plug in t equals 6. But you might want to say, wait a minute, let me slide this through until I reach t equals 6, and now let me evaluate the integral under that condition. And that way you can simply sort of solve one problem as you have already now demonstrated your ability to flip and slide. Maybe that will become more clear via an example. And with respect to sinusoidal steady state response, you're now looking at h of s and walking up the imaginary axis, or replacing s in this transfer function with j omega, or a specific frequency omega naught. And you should be able to calculate that either numerically, or what I'm saying analytically, or graphically. Know what that means to sketch it in the S-plane, sketch your poles and zeros, and then show me what the magnitude and angle might be for the pole at s equal -2 minus j5. And maybe you're looking at a frequency of 7 radians per second. I'm hoping right now you're actually sort of seeing this image of an S-domain plot. What did I just say? I said you were maybe here at no, I probably already messed up. Was I at -2 minus j5? Is that what it was? It's been a long day, but a fun day. Maybe we had a pole there, and now I said, oh, evaluate that at 7 radians per second. Now you would be looking at that angle, if I wanted the phase information, and that distance of that hypotenuse, which has sides of 2 and 12. And that would be the length of that particular pole factor's magnitude contribution. But I'm just, when I'm talking about that and saying, oh, think of what's happening in the S-plane, I want you to be comfortable envisioning, or with in other classes I've made a big deal about napkins, being able to just be at a table, maybe you're out to dinner, and somebody asks you to sketch a Bode plot. Now you pull out a napkin and you can now sketch a Bode plot. You're laughing. This may actually happen. Maybe you're trying to design a filter or design some system, or maybe somebody says, what's the behavior of this system going to look like? You pull out a napkin and you draw an S-plane and you put down the poles and zeros and you say, this is what's going to happen at that specific frequency. All right, so I guess, no, you better not be able to bring napkins. You already have 3 sheets of notes, so don't bring napkins. Ask for a piece of paper if you need some more scrap paper on the exam. But after this class, napkins are fair game. Okay? And you should know the contribution from each factor. That's sort of what I just illustrated with that S domain with one particular complex pole. But how long do you have to wait before you reach sinusoidal steady state? 5 tau. So now if you had a system, or maybe I wouldn't even give you a system. Whoops, I'm kind of getting ahead of myself, but I don't care. Let's suppose that I gave you a pole zero diagram. And I said, how long, oh, maybe I should label this. You know what? I don't like that. Let me make it -2. I give you this pole zero diagram and I say, when will the transient be gone if you now applied a step input to this pole zero diagram corresponding to a transfer function? How long would you have to wait before the transient or the impact of the transient was basically gone? I said we would design the exam tonight, right? Looks like that one might not have so many points scored on it. But what do we have? I need to get up. Stiff, sore. How many poles do we have? Pardon? So we have 2 plus, how many did you not see the first time? 2. So 2 plus 2, we have 4 poles, don't we? 4 poles and 1 0. Which of those singularities influence the transient? The zeros shape the transient, but the length of the transient is influenced by the poles. Now, which ones determine or influence the length of the transient? Do we remember the speed? This one, these two complex, what's their real part? How fast are, okay, so I'm going to change it up after I ask that question. How fast are they shaking? Their damped frequency is 4 radians per second, isn't it? So they're shaking at 4 radians per second, and how quickly are they decaying exponentially? What's the exponent? E to the minus 5t, isn't it? So these two have an e to the minus 5t associated with them. So they're going to be exponentially damped sinusoids. What's the frequency of oscillation for the pole at -4? It doesn't have a damped frequency, does it? It's a real pole. So what does it look like as far as its structure? What's its exponent? What's its contribution to the transient response or the total response? What are we going to see in our inverse Laplace transform that's coming from that pole at -4? E to the minus 4t, isn't it? This one was e to the minus 5t. This pole at -4 is e to the minus 4t. Which of those two is faster? Which one is decaying more rapidly? E to the minus 5t. So the further you're into the left half plane, the more rapid the transient, the quicker you're going to decay. Okay? What's the decay associated with the pole at -2? e to the minus 2t. You guys know this. So now you have an e to the minus 2t, an e to the minus 4t, and an e to the minus 5t. Which one is going to influence the transient for the longest amount of time? The slowest pole, which is the one closest to the imaginary axis, the e to the minus 2t. So that one is the dominant mode. That one influences the transient behavior. From this diagram, you can say, oh, I'm going to have terms that are e to the minus 2t, e to the minus 4t, e to the minus 5t in terms of exponential damping. This one is the slow one. This one is the fast one. And the slow one is the dominant one. And that's the one you would concentrate on to find how long you have to wait for your transient to be gone. So now you would say, okay, this dominant one, let me find the time constant associated with it. So in that case, you're saying, oh, I have 2 tau equal to 1. That's what governs, or that's how I can find my transient. I set that exponential equal to 1, because I'm trying to find when that really is e to the minus 1. That's one time constant. And if I let that exponent 2t, and I'm going to say 2 tau, that's going to give me what tau is. In this case, my time constant, one time constant is 1/2. In 1/2 of a second, that e to the minus 2t is going to be at a value of e to the minus 1. That's one time constant worth of decay. And I need how many time constants before I'm basically gone with the transient? 5. So now I need 5 of those tau, and I could say this is the slow, because I have 3 different time constants in that system, didn't I? I had one associated with the minus 2 pole, one at the minus 4, and one at the minus 5, and you'll find that those are all faster or shorter time constants than this one. This is now 2.5 seconds. And that would be your answer. Somebody might say, how long do I have to wait before I reach sinusoidal steady state if I excited this system with a sinusoid? You would have to wait until those transients are gone, and the dominant mode in that system is e to the minus 2t. You wait 5 of its time constants, which is now 2.5 seconds. That's how long you could wait, and then you're in sinusoidal steady state. And then you could say, oh, what am I going to be doing after I wait 2.5 seconds? Now that's when you evaluate h at the appropriate frequency, and we didn't talk about what that frequency of excitation was in this example. Is that making sense? Pardon? No, I didn't even give you what omega naught was in this problem. I didn't say, what am I going to excite this system with? I didn't give you that much information yet. I just said you were going to kick it and wait for the transient to decay or to die out. And I would have to give you a cosine or sine at a specific frequency, omega naught. You would find what that is, and then you would evaluate your transfer function at that frequency. But if I give you the pole zero diagram, can you solve the problem? If I do give you an input and I say, let's excite this system with a 3 cosine of 4t. I say now let x that what I said? 3 cosine of 4t. How long would we have to wait before we reached sinusoidal steady state? 2.5 seconds. That hasn't changed, has it? So we wait 3 seconds, and now we can say, okay, where are we going to be? Where's our output going to be relative to where our input is? And that's what our system tells us. But I sort of gave you a trick question. Because on that pole zero diagram, did I give you a gain or a magnitude value for H? All you know are where the poles and the zeros are. I didn't tell you what the gain was. I would have to tell you one more piece of information before you could answer this question completely. You could tell me how the phase was going to shift, because you would have all the poles and zero factors. But if I said you had a gain of a positive number, you'd have to be told what that gain is in addition to these pole zero factors to give me the total answer. Because right now, all you know is you know that H of S was, did we have a 0 at -3? We had a pole at 2, a pole at 4. Oh, brother. Where was this guy? Was it at -5 plus and minus J4? But what I didn't give you was that, did I, from the pole zero diagram? I would have to tell you what that was. Maybe that was 7. I would have to tell you what the gain is, or I might say the gain of your transfer function is 2 at DC. It has a DC gain of 2. Then you could back out whatever that gain is, and I'm not going to say that that 7 corresponds to a DC gain of 2. It does not. I'm almost sure. What is your DC gain for those choices of numbers? You just evaluate that at H, or at S equals 0. So now you have 7, 3 over 2, 4, an ugly number, right? 21 over, wow, 25 and 16, 41 times 8. 8/40 is 320, so 328. 21 over 328, is that right? So 30 over 330, about 1/11th, about 0.1. That wasn't too bad without a calculator, was it? What was the magnitude? Oh. Won't do that again. No more questions for me. So about 0.1, right? And that was all with a napkin, wasn't it? Right? OneNote. Okay, it's kind of an electronic napkin, but you get it. Questions on that? Yes, no? But now do you understand that I had to give you the frequency of excitation? I had to give you an X, and you had to figure out what its frequency was to determine what the omega naught was. So in this case, if I gave you this H of S, and I gave you that X of T, you would look at H of J, H of J4, wouldn't you, to find the sinusoidal steady state result. The 7 gain, that just came out of the air. I just had to pick that from somewhere. That didn't come from anything else. I just had to tell you what that was. That didn't come from anything, well, it came from magic. I just pulled it out of the air like magic. So that was not from anything that you could determine based on that problem specification. It wasn't from the pole zero diagram. I have to give you that number. Unless I give it to you indirectly and I say the DC gain is 0.5, then you would have to change that. It wouldn't be 7, it would be closer to 35 now, wouldn't it? Because we found this one with 7 was about 0.1. And if we need it to be 5 times that big, we would need to have a gain of 35 instead of 7. Approximately. Questions on that? Are you getting comfortable with these transfer functions, the poles and zeros, what you can do with them? They're very powerful. Yes, sir. So the DC gain is the same as H of 0. You're saying S is my frequency. And if we want to get it for a lot of frequencies, we evaluate or we replace S with j omega and we walk up the imaginary axis. But if we stepped right at the origin, that's J0, that's the same as 0. So the DC gain is H of 0. Questions on that? I said, wow, you're kidding me. I'm having too much fun. Do you want to do some convolution? Okay, so now I'm going to have to, I tried to prepare for this. So here is a specific problem, and I think this is from the spring of 2012 exam. Here is one of the problems. It says, suppose you're given this waveform, z of t, and it's a part of a convolution problem. Maybe this is the input that you're exciting your system with. And somewhere else in the problem statement, you're given the circuit or the impulse response. But in this problem, so read these problems very, very carefully. In this particular problem, all I'm asking you to do is find a flipped and slid version of this waveform. Just flip and slide z of t. That's what I'm asking for here. But I need you to label it. Find the functional values that are associated with this particular flipped and slid waveform. So you probably want to find the functional values on z of t first, and then figure out what they need to be in the flipped and slid version. Is it clear what's being asked? I'm only asking for the flipped and slid version of z of t. If you're thinking about this in terms of how we are solving the problem or applying this, maybe your impulse response starts at 0. So if you hit your circuit with an impulse, it starts ringing immediately if the impulse response starts at 0. And then it may have, I mean, a physical system usually has an infinitely long tail for its impulse response, but I could give you any generic signal that I say, this is your response to an impulse, and you just have to solve it. But if we now say that this input is being applied to a circuit that has an impulse response that starts at 0, when are you going to, with this time labeling, when are you first going to see an output? If you're measuring the output, you apply this as the input to a system or circuit that has an impulse response that starts at 0. So when are you going to start seeing a response? At the output. Does it look any different back here? It's just as confusing. So what is this signal? This signal is saying with the value of time equals 0 sort of scratched in the sand or drawn on the paper, this input is starting at 4 units of time before 0. It's starting at -4. So that means if the system responds as soon as you hit it, that's what an impulse response starting at time t equals 0 is doing. So as soon as you hit that system, it starts shaking. This signal is being applied at -4. So the output, you're going to start seeing it shaking at -4. Does that make sense? You're exciting the system at -4 in this time axis that you've created. Somebody could say, you know what, time 0 is right here. And this -4 is actually 2 units into t equals 0, but that's not what I'm saying. I'm saying I've now drawn t equals 0. Wow, that's mislabeled, isn't it? That should be -j2. Oh no, this is z of t. What am I doing? It's a long day. I was seeing an S-plane, wasn't I? That's not an S-plane, that's time. I need to go somewhere else, even beyond the up. Yes. No, no. So the question was, with this z of t is just the input. That's independent of the impulse response. So now you have to be told what's the impulse, and that's not a part of this problem. But if I said, oh, h of t, so this is not what you would get by solving this problem. But if I said h of t, the impulse response to the system that z of t is being applied to, maybe it looks like that. So this is saying that this system, as soon as you hit it at time t equals 0, it starts shaking. Now what I'm saying is you start shaking the system at time -4. Well, the output starts shaking at -4 if you start hitting it at -4, right? So on the exam, if you need to get up and move around a little bit, that's okay. Wait a minute. What are you doing? I'm solving the convolution problem. What do you think? What's it look like? Is that clear? This is really sort of independent of your impulse. And you now say, okay, I'm exciting the system at -4. Well, based on the impulse of this system starting as soon as you excite it, I'm going to see at the output something happening at -4. You would probably feel more comfortable if I erase this part of the diagram, wouldn't you? Then I would wait 2 seconds and then hit the system. If I erased all of this negative time part of z of t, let's just talk about that now. Now I hit the system at 2. When are you going to start seeing something at the output? At 2, aren't you? Does that make you feel better? That's really all you're doing here with z of t. You're hitting your system, but now just by the way I've labeled the time axis and the origin, t equals 0, I'm saying that this input is starting at -4 based on somebody's hypothetical or sort of pre-selected t equals 0 value. That may or may not mean anything, but it does, let's say, in this problem. Okay? Wow. So if my h of t was something else, let's say h of t, so that's when it starts, right? What if the h of t, maybe it starts at 0, but maybe it completely shuts off 2 units of time after it's been excited. So you hit this system with an impulse, it shakes for 2 seconds and then it quits. It's done shaking. That doesn't have this infinitely long tail. So now with this z of t and this h of t, when's the last time you're going to see the output shaking? Pardon? At what time t? 14? So now I'm exciting the system. The system responds like this with h of t. I'm exciting it with z of t. When's the last time you're going to see anything happening at the output? So what's the last time I'm going to excite this system? 6. After I excite it, how long does it continue to shake? 2, doesn't it? Is that making sense? So, no? Well, we need to get these things figured out, don't we? So this, if I hit it with an impulse, I hit it, the impulse at time 0, then it keeps shaking until 2 units of time later. So it's going to be 8, isn't it? So now I keep shaking this system until 6, then I quit shaking it. Well, this guy continues to shake because it has some memory. But it only shakes for 2 seconds beyond when you hit it. So when is the last output going to be seen? 2 plus 6, isn't it? 8. Is that making sense? Can I make a graph of that? Well, what you need to do is when you're solving these convolution problems, if you have finite duration lengths for your excitation x or your two waveforms, x1 and x2, then the start time is the sum of the leftmost endpoints. In this case, it was -4, -4 plus 0. And when is its end time? The sum of the rightmost values, 6 and 8. So that's a way of checking your work. If you go through this and flip and slide, you should find that you only have a non-zero y between t equal -4 and t equal +8. And beyond those two extremes, your output better be 0. So if you went through the entire convolution problem for these two pictures, that's what you should see. Now, if h had an infinitely long tail, your y is going to have an infinitely long tail, isn't it? If you hit it with some excitation. But here I clipped the tail because I wanted to get you thinking about starting and beginning and ending intervals of time for your output. So let's flip and slide z of t and then we'll come back to that question, okay? So are we ready? Well, no, if we're flipping and sliding z, wow. Did anybody bring something to snack on? The last place I was, somebody brought their dinner. I'm going, and it was a smaller room and I could smell it and I'm going, I haven't eaten. But it wasn't a pie, so I didn't have a disaster, huh? We would have had some impulses going if it was a pie. Where were we? Oh, flipping and sliding, z of t. First thing I would do is I would probably label the functional form of this. This is 2 from t equal 2 to 6. And now I need to find what this guy is as far as its functional description. And I might just extend that and say, oh, its y-intercept is 2. So now I know that z of t is something t plus 2. Is that okay? So if I did put in t equals 0, and if it continued to move up in that same slope, it would be at 2. Is that okay? And now what do I need for a slope? Or I could say, well, if this is true, then I know that it assumes a value of 0 at -2. So if I plug in t equal -2, I need to get z of t equal to 0, don't I? It's going up 1 unit for every unit of time, isn't it? Isn't the slope 1? So the functional form for z of t is now t plus 2. And when is that true? Only for values of t between -4 and -1. And it's 0 everywhere else except for this time interval when it's 2. Okay? So that's z of t functionally. Now we might need z of lambda, but z of lambda is exactly the same. We just substitute lambda everywhere where we had a t. Is that okay? But now let's look at z of minus lambda. Oh boy, now I'm going to have to remember what I just had. Whoops. And this is supposed to be my lambda axis. If I want minus lambda, I now simply rotate that around the vertical axis. So the easy part is the right part sliding or flipping over into the negative, and I'm going to go from what? I'm going to have a value of 2, aren't I? And this is going to be -6 to -2. And what's the other part going to look like? So now it's going to start at 1, and it's going to end at 4. And what's it do between those two? It's going to be decreasing, isn't it? It's going to, well, it's going to be that, isn't it? So I just flip that across the vertical axis. And I could replace t everywhere with minus lambda and get the functional form. That's z of minus lambda, but that helps me actually determine pictorially z of t minus lambda. Because now what I want to do is I want to slide or make t small enough in value negative so that this endpoint at 4 is way outside wherever my impulse might start. So I slide this, my t is my adjustable parameter. I now slide it far enough to the left so that I can now move it through and see all the overlap patterns. So I'm going to now introduce a t on all of those horizontal labels of z of minus lambda so that now I have what's that going to be? This is going to be t plus 4, isn't it? What's this going to be? Is this making sense? What? Are we okay or not? What's this left endpoint of that one? T plus 1, right? It's this guy right here with a t introduced, and the 4 was that one with a t introduced. I'm just sliding everything, so maybe I should have sketched it first. I now have this piece of the other. Oh, wow. Oh, well, this napkin going to have to ask the waitress or waiter for another napkin, aren't I? Is that okay? What's this endpoint right here? That's t minus 2, isn't it? And what's this one? T minus 6. What's this functional form right here? That better be 2. And what's this functional form? We could just go back. We could say, okay, I know it's z of t minus lambda, and I know what z of t was. Whoa, what happened to it? Oh, it was right here. So it's t plus 2. I can replace that t with t minus lambda everywhere and get the expression that I need. So this is now equal to t minus lambda plus 2. Yes. I just need to push it to the left, but I want to push it to the left so that it gets outside of wherever my impulse response is starting. In this case, my impulse response, and I didn't even have an impulse response for this question. So I'm adding on to this particular question, above and beyond what was the original question on this test. But on this question that I've added to, I said, okay, let's have this for the impulse response, h of t. So I want to make my function that I'm flipping and sliding, at least its rightmost endpoint, I want it to be to the left of wherever this one starts. And so I slid it over to the left of the vertical axis. And now I could, if I wanted to, I could slide this through, and when is going to be the first time? So now if I put this together with my impulse, y of t is going to be 0 for what values of time t? When t plus 4 stays to the left of 0, or when t is less than or equal to minus 4. Is that when we said we started to see something shake in the output? Was it t equal minus 4? So now we've just convinced ourselves that, oh, up until minus 4 in time, we're not going to see an input, or I'm sorry, an output due to this input. Now we can get back to your earlier question. If we shift that all the way, the last overlap picture that we're going to start to see here was our h of t, and then we had that, right? And we have this other piece that I don't even need to worry about because it's long gone relative to any contribution to the output because it does not overlap with our impulse response at this point in time. Y of t is the result of convolving z of t with h of t. So y of t is the output response due to convolving h of t with z of t. So now, when is this overlap pattern? So I've now gone up through all the overlap patterns, and I'm down to almost the last one. When do I get y of t not equal to 0? T minus 6 needs to be less than 2, doesn't it? Which says that t is less than 8. When t gets bigger than 8, my output's 0. Does that help a little bit? So that's why you can sort of add these endpoints when you have two finite interval signals that you're convolving. Does that help? No? Pardon? You'll figure it out. Yes. So now the question was, is there an interval in the middle where it might be 0? And that really depends on the spacing of all of these waveforms, doesn't it? And just looking at this picture, these two pictures, can you now answer your own question? Yes, there is, because I let this response of the system only be 2 units in duration, didn't I? And now, as I slide that, there is a gap, a 3-unit gap in the input. So in that interval, when I'm between -1 and 2 with this input, I shouldn't be seeing any output. And we could slide that through and see when exactly that's going to be in the output. But there is an interval of time when the output will be 0 in between -4 and 8. We seeing that? What I'm saying is now we have the possibility, as we're working through all of these overlap patterns, we didn't flip and slide H, it stayed there, but now, based on what we had labeled here, we have a T+1, and this was T+4, wasn't it? And this one isn't that what we had? Now do you see when we might have a 0 value? These waveforms do not have any overlap, do they, in this part of the sliding process and trying to identify intervals that have unique pictures of overlap. When is this going to be true? Question? So now as I'm sliding this, when I'm sliding Z through H, what's happening? I'm actually looking at unique intervals of time, T, where my Y is going to be different functionally. So this is because T is my adjustable parameter, that gives me my Y of T answers, the intervals of time. So when is this overlap picture going to be in existence? When does this occur? This is going to be true when T+1 is bigger than 2, right? And we need T-2 less than 0. If we subtract 1 from both sides, this says T is bigger than 1, and this says T is less than 2. Is that right? So there's a 1-second interval of time when Y of T, the output, is actually going to be 0 between -4 and 8. Is that making sense? Yes. So let me finish this one. We could say now Y of T is 0 when T is bigger than 1 and less than 2. So that's one of our answers in this long list. Now if I go back, what did you say here? So this case is going to be another unique pattern when this t minus 6 is going to be bigger than 0 and less than 2. Because this t minus 2 has long since passed 2 because of the width of this. This is 4 and this width is 2. You can't tell it by my drawing, but the blue is much wider in support interval than the black. I skipped all sorts of cases to get to this. I jumped to the end. I jumped all the possible overlap patterns to get to that picture. But in a convolution, you have to slide it gradually through. All of the cases. If you needed to find the entire answer, you would start with this one and then start sliding it through and see, when do I get unique overlap pictures? And then I evaluate the integral for each of those. So this was the beginning picture. This was the next to the last picture. And then I jumped back because of another question to one of the middle overlap pictures. So I didn't do this linearly or serially. This is not the way you would solve it. So can we do an example? Why don't we look, are we okay with number 5? Did we answer it? What was the question? Oh, we just needed to sketch z of t minus lambda, didn't we? So we got it somewhere. Oh, there it is. That's right. I put the h of lambda on top of it, didn't I? Okay. So that's my z of t minus lambda for its two intervals. If we looked at problem 6, all right, this is a review. If x of t and h of t are being convolved to create an output response y, state the interval of time. This is again, I think, from the spring 2012 exam. State the interval of time t when y of t is non-zero. If we forget x of t for now, what does h of t tell us about our system? If it was truly an impulse response, I hit it, does it respond instantly? No, it waits 2 units of time and then it shakes for 2 units and then it quits. Just because. This is a hypothetical. This is not necessarily a real system. Okay? This is just to see if you know how to do convolution. It may not make sense physically. But this one says I hit it with an impulse at 0. It waits 2 units of time and then it shakes. And then it shakes for 2 units. So now, with that understanding, I hit it at time t equal 1. When are you going to first see an output? Is this making sense? All right, I hit it at 0 with an impulse. When do I hear it sing? I hit it at 0 with an impulse. When do you hear it sing? At 2. And it sings for 2 units of time and then it stops. Thankfully, right? Now, we hit it at 1. When are you going to hear it sing? 3. 2 after 1, isn't it? Is that okay? Are we starting to feel okay about this? Then how long is it going to sing? When's the last time you hit it? what did you do? You basically just added 2 and 1 to get 3, and 4 and 4 to get 8, right? That's really all that you did, but the understanding was I quit hitting it at 4. It waits 2 more units of time beyond 4 before it starts moving, and it moves for 2 more units of time after it started, which it didn't start until 6, and it went to 8, just like we're going to do tonight. Okay? Is that clear? All right. So that's, now I lost my pen. Oh, you were hoping. 7, another convolution. So this one says, here are some waveforms, and you are asked to find what is the output at time t equal 5. When are you going to stop seeing an output response from this system? Never, right? Because the impulse response just keeps going. It has an infinite tail, doesn't it, for the impulse response. So if you ever excite this, you'll wait 2 seconds or 2 units of time before it starts singing, but then it sings forever, doesn't it? Now, when are you going to first hear it sing in this particular case? At 2, right? Because you hit it at 0. So you're going to hear it at 2 and then for all time thereafter. Is that clear? So you know it's going to be singing at 5, don't you? And I want just one value. I want to know what's the output at time t equal 5. And it's not necessarily instantly obvious, right? It's not a pull a number and see it. You now need to flip and slide and figure out what's going to happen when t is equal to 5. If I give you this problem, which of these signals are you going to flip and slide? H, right? That's a lot easier to flip and slide, isn't it? You can pretty easily find this functional description for x. It's just a constant slope, isn't it? Of 2, no, 1. So this is just x of t is t, isn't it? And you have to worry about that gap in there. But now if we flip and slide h, what's this going to be? T minus 2. Is that okay? Now what are we going to do? And I apologize, I'm kind of flying through these, but now we slide this up until t is equal to 5. So we're sliding this through this x of lambda. And x of lambda now goes up to 4, and then it starts again at 6, and then it goes up to 10. So this is now lambda, and this is lambda, but this is 4, 6, and 10. And we now are sliding this guy through until t is replaced with 5, or until t is equal to 5. So this guy is going to go to 3, isn't he? This is now t minus 2 evaluated at t equal to 5. And now I simply need to find the area under that curve of x of lambda and h of t minus lambda. Is that making sense? So I now start shading. I'm going to shade this one. And then I have the x, and I'm saying, okay, y of 5 is going to be this integral, and what do I have? I have the two functions, don't I? I have lambda, that's x, and then I have h of t minus lambda, but that's just 2 d lambda. And what are my limits of integration? Is that okay? And now I just have a calculus problem, an integral problem to solve. I simply say, oh, that is now going to be 2 lambda squared over 2 evaluated at 0 to 3. The 2's cancel. I have 3 squared. That's going to be 9. So y of 5 is 9. A fixed number because I replaced t. But you could, and I would recommend that you look at this solution because I worked it completely out. I didn't have anything better to do that weekend besides grading exams, so I went ahead and said, let's just work this out. But it's all worked there for you. I flipped it and slid it through all the different patterns, and then what can you do? Then you can say, oh, I have y of t that has all of these different functional forms. Let me find the interval of time when 5 is there and evaluate that y of t expression for t equal 5, and I better get 9. You could actually do this with geometry. Because what do you have? You really just have that triangle, that green triangle from 0 to 3, and it's scaled in value by whatever h was, and that was a value of 2. So if you find the area under this triangle, what I'm trying to say now, just this, for this particular value, I now have this triangle from x, and the area of that is 1/2 base times height. So I have a base of 3 and a height of 3. I have 9 divided by 2, 1/2 base times height. And I need to scale it everywhere by h, which is 2. So I have 9 over 2 times 2, 9. Same answer. I didn't have to integrate. I just solved it geometrically, if you wanted to. Does that make sense? If it doesn't, don't worry about it. Solve it the full-blown way. But I would suggest that you probably don't want to go through and find all of the cases. If you have to find the first few cases, that's okay, but I wouldn't keep going beyond 5. Once you see that the intervals of overlap are way beyond 5, I would stop, because all it was asking for was t equal 5. Yes? So now what do I want to do here? Now I want to, if I were doing this in all of its glory, I have this that's fixed, isn't it? But now I have h that comes in, and what was this endpoint? Was that t minus 2? There's the first overlap pattern, which is no overlap, right? The next one, and when does that overlap occur? When t minus 2 gets bigger than 0, and when t minus 2 is less than whatever this was. Was that 4? So now I get this overlap pattern for t greater than 2 and t less than 6. But this one up here was true as long as t minus 2 remained less than 0, or when t was less than 2. And this gave me an answer of no overlap or 0. This one, what's my integral here? Let's just see if we can, y of t now. Functionally, what's the integrand? I still have lambda, right? And then I have 2. What are my limits of integration? And it's true as long as t is bigger than 2 and less than 6. Are we getting this? Does that make sense? So I evaluate that integral, which all your integrals are going to be very similar in evaluating. You'll just have to, in integrating, and then you'll have to integrate or evaluate them. Not going to make it to 8. The impulse response, it's not a duration of 2. Sorry, units of hours. Poor joke. But do you get what I'm saying here? My battery pack may be dying. Mine, not the microphones. Questions on this, on convolution? Do you see how, and I would just say go look at the solutions, but it just progresses like that. And you can see the different patterns that you're going to be presented with. This one now has an infinitely long tail. So you're really just going to be watching this, and eventually you're going to have total overlap. When will you have total overlap? Can you see that by just looking at this picture? This is 10, wasn't it? You need t minus 2 bigger than or equal to 10. So as long as t is bigger than 12, you have total overlap. And now you're just going to have the area under that blue triangle, the area under that blue trapezoid scaled by 2, and that will be your value from 12 all the way to infinity. You'll have a constant output. Because the integral is just finding the area under curves. Yeah. What you tell me. I think the question was, if I now slide this h of t minus lambda over to the right, such that t minus 2 is bigger than 4, but less than 6, do I get a non-zero output? Can you see? What? Here's what I thought we were asking. Do you get any non-zero value when that rightmost edge of the red curve, t minus 2, is beyond 4 and less than 6? Do you get a non-zero value? And now you're saying, do I have cross-hatching? Not just hatching, but do I have cross-hatching? Are they overlapping? And indeed you do, don't you? You have the area under this scaled by 2. So it's 1/2 base times height. Your base is 4, your height is 4. That's 16 divided by 2, scaled by 2. So from this point, from 6 to 8, you have a constant output of whatever I just said, 16. Is that? And then when you start to get beyond 6 with t minus 2, then you start introducing more area. And you may want to do 2 different integrals. These are the questions you need to ask. Is that everybody experts on convolution? I want to see hundreds on all the convolution problems. I'm going to be disappointed? No, I'm not. You're going to go home and really get this stuff.
So the rectangle one
So no, the response is y, isn't it? Y of t is the response, which is the product. What are you doing? You're actually taking this h right here and scaling it by that value of x. Then you're taking this and scaling it by that. You're taking this and scaling by that. So you now have basically enhanced that triangle by a scaling factor of 2 at every point, and you're finding the area underneath that scaled triangle in this particular example. Because your convolution is the product of x with h of t minus lambda. Point for point, and that gives you maybe some weird function, but you now find the area underneath that function, and it might be a function of time. Yes?
So using the area and the scaling in order to find the integral only works if it's constant.
If it's, so the question was that scaling and doing it geometrically, that only is nice to do when your geometric shapes are cooperating. Here you have a triangle and a flat, and those are pretty easy to sort of put together. If you had two flats, you could do it, right? So it's just, if it makes sense geometrically, you could do it that way. But I would probably, for now, for starters, I would do it the equation or formula way. And then maybe if you had time, you could say, does this make sense? I think this is just a geometric problem. Check it geometrically, maybe at a few points, and you go, oh, yeah, I'm feeling pretty good about this. The other thing that you need to realize is that convolution is continuous. If you now have an interval of y for, let's say, that stops at 4, and then another one that starts at 4, if you evaluate the waveform y of t at 4 in both of those overlap patterns, you better get the same number. Did that make sense? If you had y of t equaling all sorts of different functional forms, let's say it was 0 for t less than 5. Oh, and this is a new problem. And maybe it was t minus 2 for t bigger than 5 and less than 7. I'm going to run into problems. That's not right, is it? So this needed to be what? 2, didn't it? To be 0. Whoa! So I should have changed the other thing. Is that okay? Then what would it have to be at the next interval? Now if this was 7 up to, I don't know, 10, then we know that whatever this is at 7, it better evaluate to what value? 5. Is that okay? These need to be consistent and they're continuous as you transition between the two. And if you do quick checks and you find inconsistencies, I would write a note and say, I must have made a mistake or an algebra error. At least show me, demonstrate to me that you know that something is amiss, instead of saying, oh, I hope he never figures this out. Hope he doesn't see this. Then I'm going to say, he didn't see this. Minus 25, it was worth 10. It's not funny anymore, is it? Never was. Okay, good. Questions? Wow. We really concentrated on convolution, didn't we? Yes? So now you've basically scaled the green triangle by the red constant value. So in this one, you are integrating the whole area underneath that green triangle, and scaling that area by 2. That red says scale everything by 2, everywhere in that interval of time from 0 to 4. If this isn't making sense, I wouldn't spend any time on it. I would just say, let me do the functional evaluation and hope that that's correct. This is just another way to check your work. So I wouldn't worry too much about geometry at this point. And we can talk maybe. Anybody have a question on something else that you're willing to ask? But you need to know more than just convolution. I had other problems here. Sketch the S-domain equivalent circuit. You're okay with that, aren't you? So if I sketch this, and you would need to put in the initial conditions, and now you may not know them, so you would just put them in as I sub L of 0 minus and V sub C of 0 minus. I didn't say anything about what the initial conditions are, so you would have to introduce those explicitly. You don't have the values, you can't find the values without a V1 given or some other switches available. But you can assume that somebody energized the inductor and the capacitor and then said, oh, those were your initial conditions at 0. Then you have to incorporate those. And if you were doing mesh analysis, you would have SL in series with a voltage source with the appropriate polarity and the appropriate value. That's a function of your initial condition or the initial inductor current. Similarly with your capacitor. So in this case, how many mesh currents are you looking at? I'm 3. I didn't ask you to solve it, did I? I just said draw the S-domain equivalent circuit. You just draw the circuit with initial conditions in this case. What was another one? Find the transfer function. All sorts of ways to find this, but if it's transfer function, what do you do with initial conditions? You don't need to worry about them. You just replace L with SL, your C with 1 over SC, do the analysis. Maybe you do a 2-mesh analysis. And you find your second mesh. What were you asked for? If you find the current in the second rightmost mesh, that's your output. And you write that in terms of your input voltage, V sub 1. These are initial condition and final value. Those aren't too interesting. You need to be able to do those. Here is one that we kind of talked about before, I think. I give you a transfer function. Then I say find the phase angle associated with the complex 0 of H of S that is located at -1 plus J2 when omega is 4. Is it clear what we're doing? You don't even have to draw your whole pole 0 diagram. You just need to worry about the 0 that's in the second quadrant. Now you have, whoa, what am I on? Now you have -1 and J2. There's a 0. And you're asked to find what's happening right there. Was it the angle? What's that phase angle? It's not 4, is it? It's the change in that, which it only had to go up 2, didn't it? Does everybody see that? Only went up 2 from that horizontal real line that I measure my angle with respect to, and I went over 1. So the inverse tangent of 2. Is it positive or negative? It's positive because it's a 0. It's upstairs. If it was a pole, you would find the angle, and then you would say, oh, that's a pole, so I need to negate that angle. Is that clear? You guys are going to just ace this exam. What's this one? Find the transfer function between I1 and V sub 0. Maybe you do a source transformation over here. Maybe not. You can do it however you want, right? You could have another node voltage here if you wanted, and this voltage. Or you could just do this node voltage and say, oh, I'm going to have this as a complete impedance, and then solve for this current coming here and scale it by that capacitor impedance to get V0. So you just have one unknown voltage to solve for. Again, I think I worked this many different ways on the practice exam. So you can solve it however you want. I'm not telling you how, I'm just saying find the transfer function. And there's many ways of solving this. You could even do 2 meshes. You know this current, don't you? It's I1, which is the known source. And then you find I sub 2. I think you guys have had very good patience. I hope this was helpful. But you really need to know the convolution. I really want you to be convolution pros when you get done with 320A. Okay, I'll see you Thursday. I do have off. What's tomorrow? Wednesday? I have office hours from 2 to 4 and Thursday from 11 to 12. 3:45, that's correct, because I have a class at 4 tomorrow. Thank you. So 2 to 3:45 tomorrow.